discussing some problem like mixed flow reactor and Plugflow reactor in series in this class. Here we are talking about a system where there are two different reactors are in series. One liquid reactant stream of 1 mole per liter is going into through these two mixed flow reactors. Both of them are actually mixed flow in series. The concentration in A exit of the first reactor is 0.5 mole per liter. So essentially this is from first reactor, it is coming out 0.5 mole per liter. Find the concentration in the exit stream of the second reactor, that is second reactor out, that is C2 we are asking. The reaction is second order, it is given with respect to A, and V2 volume of this one and volume of this one. The ratio is 2, V2 by V1 is 2. The initial reactant concentration is given, C0 is 1 mole per liter. So this is the diagram and this is the problem. We have to find out C2. So how to deal with this problem? This problem can be solved independently because there are two only reactors are involved. So for example, in case of reactor 1, C0 is the input, C1 is the output. For reactor 2, C1 is the input and C2 is the output. So we'll try to do the problem solving here in terms of concentration. So for each reactor, what we know, let's see, we know tau I equal to Vi, volume of reactor, divided by flow rate. So U is the volumetric flow rate, liter per minute. Vi is the volume, maybe liter. And how it can write? We can write concentration I minus 1. Before that, what is the concentration at the exit of the reactor divided by minus Ra. Minus Ra is the rate of reaction here, which is already given as second order. So I can write K into Ci square. So this is valid for first one also. For first one it will be like tau 1 equal to C0 minus C1 by K C1 square. For 2 it will be like 2, that's all. So it is a general for first one, second one, and we are keeping this V and U unchanged there, and A is the volume for each of the reactors separately. So if I am having two reactors, we can do the same thing for V1 by U for first, C0 minus C1 K C1 square. For second, V2 by U equal to C1 minus C2 into K C2 square. So we'll now what we will do, we will divide equation 1 and equation 2. So I can write, for example, this one I am dividing by this one. So V2 by V1, because U will anyway cancel out, K will also cancel out. It will be C1 minus C2 by C2 square, C1 square divided by C0 minus C1. So by the way, you already know C0 and C1 values. So we'll plug it C1 values whenever you know C1 and C0. C0 also we know in this case. So C0 is actually 1. So this is known. Unknown is only C2. That's all. So C2 remains unknown. And V2 by V1, that ratio is already given, that is 2. So it is very easily, now it is simply a mathematical problem. So just rearranging, I am not showing you the rearrangement, you can do it yourself. So V1, V2, ratio is 2, so remaining is C2 terms. So 4C2 square plus C2 minus 0.5 equal to 0, and it is a quadratic equation. You can really solve it, and so once we are solving, C2 is coming as 0.25. So this concentration C2 we can find out by making a comparison of the two reactor systems. Simply the performance equation, you need to always keep in mind the definition of tau, the expression in terms of concentration, in terms of maybe the fraction converted X. Anyway, you can do it in the same approach. So here both of the reactor are mixed flow. Now we'll take another new example here, 6.2. Here an aqueous stream concentration is given, passes through a mixed flow reactor followed by a plug flow reactor. So there are two things are there. Find the concentration at the exit of plug flow reactor, means finally if if the mixed flow reactor concentration is 1 mole per liter and the reaction is a second order with respect to A, and the volume of the plug flow unit is 3 times that of the mixed flow. Very similar. Only thing is that in this case the diagram will be a little bit different. Here one is mixed flow, another is plug flow. Plug flow volume is 3 times larger. C0 is given 0.4. In between them intermediate volume is, if the mixed flow reactor concentration is given, so that concentration, that is actually C1, is given 1 mole per liter, it is known. C2 is unknown, so the problem remains very similar, though the perspective will be different, or the expression will be different here. So for mixed flow reactor we already know V1 by U C0 minus C1 by minus RA. We are assuming here this reaction is going to be second order. Okay, so K into C1 square, because here concentration is C1, you try to understand. So C0 minus C1 by KC1 square, and for the second part, the plug flow, it is, I am assuming the volume is V2, so V2 by U will be always same because they are in series, so same flow rate is there, equal to minus concentration of input to the plug flow, concentration coming out of the plug flow, dCA by minus RA. So this minus RA is already known, KC1 square, so we can write KCA square. Concentration is, starting concentration for the plug flow, here you can see starting concentration input is C1 and output is C2, so C1 to C2. So I will write the limit for C1 to C2 dCA by K CA square. So this integration you can do. So essentially the expression will come as 1 by K into 1 by C2 minus 1 by C1. So both the case we found out V1 by U, here V2 by U. This is the expression and here this is the expression. We can compare them, now divide them. So we can say V2 by V1, second equation I am dividing by the first one. So it is becoming 1 by K, 1 by C2 minus 1 by C1, and dividing by this, so it is going up, and C0 minus C1. Now we can plug the C0 and C1 values once again. So C1 I know, C0 also we know, and C2 is only unknown. If we plug them all together, and K is anyway cancelling out, this K and this K is cancelling out, so the whole block of this derivation is becoming simplified. And V2 by V1 you already know, that is actually 3 times, so V2 by V1 is 3. So what is happening, 1 by C2 minus 1 is becoming 9, so C2 is 0.1. So you see we have derived the expression for one or more reactor in series, but we are actually dealing independently, separately. But that separation way we can do only for few reactor. If it is number of reactor is more than 2 or 3, probably this way it will be too complicated to solve, and that's why we need the expression as I have shown earlier. The next problem will be a little bit different in terms, because here we will show you a little bit larger assembly. Let's see the problem here. Here reactant A is being converted to R with initial concentration 26 mole per meter cube, passes steady flow through 4 equal size mixed flow reactor in series, where total tau is 2 minutes. Total tau 2 minutes means we know for any individual one what will be the tau, so it's 1/4, because n tau is 2 minutes. When the steady state is achieved, concentration of A is found 11,521 mole per meter cube in the 4 units, so we know concentration for this reaction. So we don't know what kind of reaction it is, we don't know what is the order. What must be tau plug so that we can reduce concentration from 26 to 1 mole per meter cube? So they have given the whole problem in terms of 4 equal size mixed flow reactor, and finally asking if we use to 1 plug flow reactor, what should be the tau values. So that is the query in this problem. Now we are making a drawing of this for better understanding. So 1, 2, 3, 4 we have shown here, and concentration is given, input is 26 as you have already given. Then in the reactor 1 the concentration is 11, so that's why 11 is going into second reactor. From second reactor where concentration is 5 is going to third. In third reactor concentration is 2, which is going to fourth reactor. Fourth reactor concentration is 1, so that's why fourth reactor output is 1. So that is known. So how this information is important to us, let's see. So we already know what is the performance equation for mixed flow reactor. So each of the any one of this mixed flow reactor can be modeled. So any reactor tau y equal to V by U, because their volume is all same, so I am skipping V, and flow rate, volumetric flow rate must be same. What is it? V by U tau equal to Ci minus 1, that is the input to that particular reactor minus outflow or the concentration in this particular reactor divided by minus RA. That's all. Now if we do the same calculation approach in all the 4 reactor system, what we are going to get? Now in each of the reactor you already know tau I, total tau is 2 minutes. So for each reactor it is actually 4 reactor it is 2 minutes, so it is 0.5 minute tau I. For each reactor I know input and output. So for each reactor I will be able to calculate what is the minus RA values. And in each reactor I also know the concentration, that is Ci. So what I will do, I will use just rearrange. So minus RA, the rate expression equal to concentration difference input and output divided by tau. Tau is known, concentration input known, concentration output known. So for all the 4 reactor we will try to find out what is the RA values from simple algebraic calculation. So for example in the reactor 1, what is the concentration here? Concentration is 11, because 11 is going out and going to second. So here concentration is 11. So concentration is 11, and what is the rate? Rate is 26 minus 11 by tau. The tau value already we know 0.5, so 26 minus 11 by 0.5, so value is coming 30. Similarly for second reactor we can also find out concentration in second reactor is 5, so 5 concentration. Rate is 11 minus 5 divided by 0.5, that is 12. Then third reactor also will do, concentration here is 2 and rate is 5 minus 2 divided by tau, so 6, and the last one is 1, and rate is getting. So what we are getting here essentially concentration versus rate data. So why it is useful? Because if we know rate and concentration data, we can find out the order of the equation, which order, first order, second order, we can estimate, right? We have learned all those aspects earlier. So it can be nth order also possible. So but before doing anything we are assuming if it is first order. Let's see, if it is first order, then the rate RA equal to K into C, concentration. That means here we already know the rate and we know the concentration corresponding. If they are first order, so they should fit a straight line, and we are just verifying that only. So we are plotting this concentration value Ca and what we calculated the RA, we are plotting, and we see their 4 point is giving fairly good straight line. R square value is 0.99, in fact very good. And y, the RA equal to mx, so m slope 2.6755, that is RA equal to K into Ca. So actually from this regression we can find out what is the value for K. Of course in graph paper you need to calculate the slope also. Here it is pretty easy. So we are actually getting, we understand the two things. Yes, the equation, the kinetics is first order, and we also find out what is the K values, rate constant for the first order reaction. So K is known. So that is the only information we expected from the whole 4 of the mixed flow reactor data. The summary is that we know it is first order and we know what is the value for K. That's all we are going to use. Now we are going to come into our original problem that we are talking about is a plug flow reactor. So anyway, we already discussed that expression will be 2.67 into Ca, Ra value we can write now. Now if we go for plug flow, so tau plug flow, what is the equation? Minus Cai to Cae final, initial final expression is dCa by minus Ra. So minus Ra we already know now, minus Ra equal to K into Ca, and K value also we know, so it is becoming dCa by Ca, so ln Ca, and limit is initial concentration 26, final concentration 1. So for plug flow system it will be 26 to 1, this integration you have to do. So we found out tau p values, tau p is becoming 1.217. so that's all.